For more than a century, physicists have been fascinated by dark openings, with the idea building up some momentum around 1916. These vast inconsistencies are among the most enthralling and baffling peculiarities we know, sitting at the convergence of huge gravitational forces and an unconventional imperceptibility beyond our grasp. A dark opening, possibly gauging as much as 2 to 4 times the mass of our Sun, remains a secretive presence in the universe. Despite many years of intense research, our comprehension has expanded from almost no information to sorting out more details, with even more discoveries being made recently. A breakthrough by Michio Kaku has unveiled alarming insights about the interior of dark openings, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information opens doors to deeper investigations into what might have been overlooked so far. Join us as we venture further into the fascinating universe of dark openings and uncover what's hidden inside. The universe is vast and ever-changing. But what exactly are dark openings? Before we dive into the latest findings by Michio Kaku, it's essential to revisit the basic understanding of dark openings. While most of us have a general sense of what a dark opening is, some key elements remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of dark openings. At the time, the idea was purely theoretical. It was only about 50 years later that evidence was found confirming that dark openings are real objects in space. This discovery came during the 1960s while studying the star X1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not only moving randomly, but were also being pulled into a dense, invisible mass. This mass, later identified as a dark opening, transformed our perception of the universe. The discovery was groundbreaking, proving that dark openings were not mere figments of Einstein's imagination, but tangible, elusive entities worthy of further investigation. Following this momentous finding, scientists worldwide embarked on a global quest to uncover more about dark openings. Their efforts led to the realization that the Milky Way alone may contain around 100 million dark openings. However, due to the difficulty in detecting them, this estimate remains uncertain. Despite the fact that dark openings are incredibly challenging to pinpoint, scientists believe that many of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Understanding gravity and dark openings. Dark openings exert such immense gravitational forces that anything entering their vicinity is pulled into a singularity, a point where the laws of physics, as we know them, cease to function. In simpler terms, dark openings resemble giant vacuum cleaners, sucking everything into them. One of the most terrifying aspects of studying dark openings is that if someone were to fall into one, they would be stretched infinitely and become a singularity, their body torn apart by the extreme gravitational forces before reaching the point of complete annihilation. It's best to stay far away from one. However, dark openings are scattered across the universe. Despite the nearest one being nearly 500 light-years away, its proximity still raises real concerns. The first image of a dark opening. In 2021, scientists achieved a historic milestone by capturing the first-ever clear image of a dark opening, M87. This achievement was the result of numerous nights spent taking photographs and aligning them to create a single, coherent image. As more data was gathered, researchers discovered that dark openings consist of 3 distinct layers, rather than being mere empty voids as commonly misunderstood. 1. The event horizon. This marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the dark opening. 2. The photon circle, a region where light itself becomes trapped, unable to escape due to the immense gravitational forces at play. 3. The singularity, the core where all matter is compressed into an infinitely small point, causing the very fabric of reality to collapse and the known laws of physics to break down. What's even more fascinating is that every dark opening is unique. While they follow the general 3-layer structure, their behavior can vary significantly, making them especially difficult to study. Traditional scientific methods don't apply when investigating dark openings, so scientists must resort to indirect means, such as observing radiation emissions or analyzing the gas and dust swirling around them. Sending a probe directly into a dark opening is virtually futile, as anything crossing the event horizon is inevitably pulled into the singularity, where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on missions doomed to fail before yielding any useful data. Consequently, researchers are forced to study dark openings in 2 dimensions, despite their 3-dimensional nature. The formation of dark openings. Adding to the complexity of dark opening research is the fact that no 2 dark openings are identical. Theories about their origin suggest that they may form when massive stars collapse in on themselves. As a star consumes its fuel, it eventually loses the ability to generate enough energy to counteract the inward pull of gravity, leading to its ultimate collapse into a dark opening. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of dark openings, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful vortex of hydrogen gas spinning at astonishing speeds of 1.2 million miles per hour. The outward force should have caused this gas to disperse, yet it remained intact, suggesting the presence of a massive object at its core, most likely a dark opening. This object is believed to have a mass up to 3 billion times that of our Sun. The wormhole hypothesis. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating dark openings. He argued that instead of collapsing into a point, as previously believed, rotating dark opening forms a thin, ring-like structure known as the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws near dark openings. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could serve as a shortcut through space-time, connecting distant regions of the universe, or even parallel universes. To grasp the concept of a wormhole, it's important to understand space-time as described in Einstein's theory. Space-time is a 4-dimensional fabric warped by objects with mass. This warping creates gravitational fields that influence the motion of other objects. Imagine space-time as a sheet of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, an entry through space-time that could connect distant locations almost instantly. Although wormholes are purely theoretical, with no direct evidence supporting their existence, they are a natural consequence of general relativity. However, wormholes are inherently unstable. Physicists have long sought a theory of everything, TOE, a single framework that unifies general relativity, which explains gravity and large-scale cosmic phenomena, with quantum mechanics, which governs the behavior of subatomic particles. Despite significant progress in both fields, these 2 fundamental theories remain incompatible when applied to extreme environments such as dark openings and wormholes. A breakthrough in TOE could revolutionize our understanding of space, time, and gravity, possibly revealing new insights into the nature of singularities, the infinitely dense cores of dark openings. Some of the most promising candidates for a unified theory include 1. String theory suggests that all particles and forces arise from tiny vibrating strings in higher dimensional space. 2. Loop quantum gravity, LQG, proposes that space and time themselves are quantized, meaning they consist of discrete building blocks. 3. M theory, an extension of string theory that suggests the existence of multiple dimensions beyond the 4 we perceive. Each of these theories offers a different perspective on the fundamental nature of the universe, but none have yet been proven. M. Yakubu's recent work suggests that dark openings may hold the key to bridging the gap between these theories, as they represent the ultimate testing ground for both gravity and quantum effects. The quantum side of dark openings. One of the most perplexing aspects of dark openings is their interaction with quantum mechanics. Stephen Hawking's famous discovery of Hawking radiation in 1974 suggested that dark openings are not entirely black. Instead, they slowly emit energy in the form of radiation, causing them to evaporate over immense periods of time. Hawking radiation arises due to quantum fluctuations near the event horizon, where virtual particle pairs constantly pop in and out of existence. Occasionally, one particle falls into the dark opening while the other escapes, leading to a gradual loss of mass over time. This discovery created an even bigger paradox, the black hole information paradox. General relativity suggests that anything falling into a dark opening is lost forever. Quantum mechanics insists that information cannot be destroyed. If dark openings eventually evaporate due to Hawking radiation, what happens to the information about everything that has fallen inside? This paradox remains one of the biggest unresolved mysteries in modern physics. Some researchers believe that information might be stored in the event horizon, while others propose that dark openings may act as gateways to other regions of the universe. Are wormholes the answer? One possible resolution to the information paradox involves wormholes. Some theories suggest that information entering a dark opening doesn't disappear, but instead travels through a hidden wormhole and emerges elsewhere in the universe, or even in another universe. This idea aligns with recent developments in quantum physics, particularly the ER equals EPR conjecture, proposed by physicists Juan Meldacena and Leonard Susskind. This theory suggests a deep connection between wormholes, Einstein-Rosen bridges, or ER, and quantum entanglement, EPR, after Einstein-Podolsky-Rosen. According to this view, if two particles are entangled, they may be connected by a microscopic wormhole. If dark openings are linked by quantum entanglement, they may also be connected by hidden wormholes. This radical idea suggests that space itself could be woven together by a vast network of quantum wormholes, creating a cosmic web that connects distant regions of the universe in ways we cannot yet perceive. The future of dark opening research. The study of dark openings and wormholes remains one of the most challenging frontiers in physics. With the advent of new technologies, such as the James Webb Space Telescope, JWST, and future gravitational wave detectors, scientists hope to gather more evidence about these mysterious cosmic phenomena. Upcoming research will focus on studying gravitational waves from dark opening mergers to better understand their structure, testing quantum gravity theories using data from high-energy astrophysical events, simulating dark openings in laboratory conditions using advanced quantum computing. Yacobu's latest findings suggest that our understanding of dark openings is on the brink of a major transformation. Whether through new observations, quantum experiments, or theoretical breakthroughs, the next few decades could reveal answers to some of the most profound mysteries of the universe. One thing is certain: dark openings are not just cosmic voids, but laboratories of the extreme, offering us a glimpse into the deepest secrets of reality itself. One promising possibility for this hypothesis is superstring theory, which proposes that subatomic particles are really little vibrating strings. The hypothesis suggests that these strings make up the universe's texture, explaining gravity as well as the peculiarities surrounding black holes and wormholes. However, superstring theory also requires the presence of additional dimensions of spacetime that are so small they are difficult to detect with current technology. Despite these challenges, the quest to understand black holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Going forward, the search for superstring theory and other theories aiming to unify the forces of nature remains an ongoing challenge. However, it holds the promise of unlocking new insights into the very nature of reality itself. These theories suggest that the universe consists of more than the familiar three dimensions of space and one of time. In fact, they propose that extra dimensions exist. Nevertheless, these dimensions are so microscopic and compact that we cannot observe them directly with current technology. However, their existence could provide a key to understanding phenomena such as black holes, wormholes, and the deepest secrets of the universe. Superstring theory presents a fascinating image of the universe, suggesting that all matter and forces are manifestations of tiny, vibrating strings. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle. Just as a guitar string produces different musical notes depending on how it vibrates. The fundamental particles of nature could thus correspond to different vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the structure of the universe. This could potentially provide answers to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together make up the majority of the universe's mass and energy, yet remain largely mysterious. Yet, despite its elegance and promise, superstring theory remains unproven. One of the major obstacles in testing this theory is the fact that the extra dimensions it predicts are so microscopic that they are beyond our current observational capabilities. Detecting these dimensions would require instruments of extraordinary sensitivity and precision, and even then, the evidence might be indirect. This makes superstring theory a challenging topic to test using conventional scientific methods. However, its mathematical beauty and internal consistency make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other approaches that could lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to merge the principles of quantum mechanics, which govern the behavior of subatomic particles, with general relativity, which explains the behavior of massive objects like planets, stars, and black holes. The hope is that by unifying these two theories, scientists can gain a clearer understanding of how gravity operates at the quantum level and, in turn, gain deeper insights into the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is particularly crucial when studying black holes, as the extreme conditions near a black hole's event horizon, where gravity is exceptionally intense, demand a theory that can account for both quantum and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most puzzling and extreme environments in the universe. The singularity represents a point where space-time becomes so warped that the standard laws of physics break down. Understanding what happens in such a place requires a theory that reconciles quantum mechanics and general relativity. This has led to the development of ideas such as loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and provide a more complete picture of black holes. As we continue to investigate the mysteries of black holes, one thing is certain. The more we learn, the more we realize how much there is still to discover. Black holes are not merely regions of destruction, but are also places of incredible complexity and potential. Whether they serve as gateways to other dimensions, as some theorists suggest, or hold the key to understanding the deepest secrets of reality, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be refining our methods for observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future studies are likely to yield even more discoveries. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of a black hole shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, we will likely be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the universe. The study of black holes is not just about understanding these strange objects in isolation. It is also about uncovering the fundamental workings of the universe. Black holes are central to our understanding of space-time, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves, but also about the laws that govern the universe at its most extreme scales. Conclusion: the exploration of black holes is one of the most exciting and challenging fields in modern physics. With each new discovery, we come closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to captivate both scientists and the public alike. As we probe the universe's most extreme and enigmatic objects, we are forced to confront fundamental questions about the nature of space-time, existence, and reality itself. In doing so, we may be on the verge of unlocking some of the greatest secrets of the universe, perhaps even discovering answers to questions that have eluded humanity for centuries.